Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. 19th century Europe was an age of steam, steel, and statistics. A profound desire for certainty, for quantifiable predictability, animated the era's intellectual spirit. From the sprawling factories of Manchester to the burgeoning insurance houses of London and the sociological surveys of Paris, a new world was emerging that demanded mathematical tools to manage its complexity. The burgeoning fields of engineering and social science looked to mathematics for a kind of practical oracle, one that could forecast outcomes, manage risk and impose order upon the apparent chaos of large systems. The discipline of mathematics itself, however, often seemed to pursue a different path, one of abstract perfection and internal logical consistency, far removed from the clamor of the industrial world. Into this intellectual landscape stepped Pafnuty Chebyshev, a figure whose work would build a powerful and enduring bridge between these two realms. He was a mathematician whose mind operated with the rigor of a pure theorist, yet whose instincts were perpetually drawn to the tangible, the approximate, and the useful. Chebyshev's intellectual character was forged within the unique environment of the St. Petersburg Mathematical School. This institution, while young compared to the ancient centers of European learning, had cultivated a distinctive ethos under the guidance of figures like Mikhail Ostrogradsky and Viktor Bunyakovsky. The school championed a vision of mathematics that was deeply integrated with mechanics, physics, and engineering. Theory was seen as a tool for solving concrete problems, and practical challenges were viewed as the most fertile ground for theoretical innovation. Bunyakovsky, Chebyshev's own mentor and a leading probability theorist, had translated the foundational French works on the subject into Russian, infusing the local academic scene with the latest ideas. It was in this crucible, where abstract analysis met the material demands of ballistics and steam engine design, that Chebyshev developed his signature style, a relentless pursuit of explicit bounds, effective estimates, and powerful inequalities. His work would consistently reflect this background, always seeking answers that were less about absolute existence and more about tangible magnitude and practical consequence. His first monumental contribution addressed a central weakness in the foundations of probability theory. The field was attempting a difficult transition, moving from its origins in games of dice and cards to a more robust scientific discipline. The key concept facilitating this evolution was the law of large numbers. In its earlier forms, articulated by Jacob Bernoulli for binary outcomes, and later generalized by Simeon Denis Poisson, the law stated that the average of a sequence of random trials would converge to its expected value as the number of trials increased. This principle was philosophically profound and practically essential. It was the mathematical soul of the insurance industry, the justification for statistical sampling, and the reason one could speak of a human lifespan as a meaningful average. Yet, the existing proofs of this law were cumbersome, and more critically, they relied on restrictive assumptions about the nature of the random variables involved. Bernoulli's proof, for instance, was specific to what we now call binomial distributions. For probability to become a truly universal language for science, it needed a law of large numbers that was far more general, supported by a proof that was both simple and powerful. The problem was one of scope and rigor. How could one guarantee this convergence for any arbitrary distribution of outcomes without knowing its specific shape or form? How could one quantify the likelihood of deviation from the average in a universal way? Chebyshev's answer, presented in an 1867 paper, was an intellectual masterstroke of stunning simplicity and profound implication. He introduced a tool that has since become a cornerstone of modern statistics, Chebyshev's inequality. The inequality provides a direct, unambiguous link between the variance of a distribution, a measure of its spread or dispersion, and the probability of an observation falling far from the mean. In essence, it establishes a fundamental limit on how unlikely a random variable can be. Verbally rendered, the inequality states that for any random variable with a finite expected value, which we can call μ, and a finite non-zero variance, which we can call sigma squared, the probability of that variable, taking a value whose distance from the mean is at least some positive number, k is always less than or equal to the variance divided by k squared. This is a remarkably powerful statement. Its genius lies in what it does require: only the mean and the variance, two readily computable quantities. Its power resides in what it omits: any reference to the specific type of probability distribution. Whether the data follows a bell curve, a uniform line, or some bizarre unknown shape, the inequality holds true. It provides a universal worst-case bound, a guarantee etched into the very logic of probability. Armed with this elegant new weapon, Chebyshev turned back to the law of large numbers. Where previous proofs had required pages of intricate combinatorial arguments, his was a model of analytical economy. He considered the sample mean of a large number of independent, identically distributed random variables. The expected value of this sample mean is, of course, the true mean of the underlying population. The variance of this sample mean, crucially, shrinks as the sample size grows. By applying his own inequality to this sample mean, Chebyshev demonstrated with irrefutable logic that the probability of the sample average deviating from the true mean by any fixed amount must approach zero as the sample size increases to infinity. This was the generalized weak law of large numbers. Its proof was a few lines of algebra, yet its impact was immense. He had provided the rigorous general foundation that the field desperately needed. He had shown that the convergence of averages was an intrinsic property of randomness itself, a universal law applicable to phenomena across the sciences. This achievement transformed probability from a collection of special cases into a coherent mathematical theory. It provided the mathematical certainty that allowed actuaries to confidently set premiums, knowing that over a large pool of clients, the collective reality would hew closely to their calculated expectations, a piece of mathematics that underwrites the very concept of shared risk. The legacy of this work is foundational. Chebyshev's inequality is often the first encounter a student has with a distribution-free result, a powerful class of methods that form the basis of non-parametric statistics. It remains an indispensable tool in fields where underlying distributions are unknown or untrustworthy, from financial risk management to industrial quality control. It provides the ultimate safety net, a conservative estimate that, while perhaps loose, is unfailingly reliable. Having thus established a new framework for imposing a predictable order upon the world of chance and large numbers, Chebyshev's analytical vision turned toward a domain of mathematics characterized by a far more ancient and enigmatic form of disorder, the mysterious and seemingly chaotic distribution of the prime numbers. The framework of predictable order he had imposed upon the world of chance and large numbers now faced its antithesis. Chebyshev's analytical vision turned toward a domain of mathematics characterized by a far more ancient and enigmatic form of disorder, the mysterious and seemingly chaotic distribution of the prime numbers. For centuries, the primes had stood as the fundamental, indivisible atoms of arithmetic, yet their sequence appeared to follow no discernible pattern. They were a source of both fascination and profound frustration. By the mid-19th century, a powerful piece of mathematical intuition, a conjecture formulated independently by Carl Friedrich Gauss and Adrien Marie Legendre, had taken hold. They proposed that the number of primes less than or equal to a given value x, a function denoted as pi of x, could be approximated with remarkable accuracy by the expression x divided by the natural logarithm of x. This assertion, which would become known as the prime number theorem, was one of the great unsolved problems of the age. It was empirically verifiable. One could count primes and check the formula, and the correspondence was astonishing. Yet a formal proof remained completely out of reach. The core difficulty lay in the very nature of the prime counting function itself. Pi of x is a step function. It remains flat for stretches of integers, and then abruptly jumps up by 1 each time it encounters a prime. This discrete, jagged behavior made it fundamentally incompatible with the powerful, continuous tools of calculus and analysis that had revolutionized other areas of mathematics. The problem was akin to trying to describe the precise path of a jittery insect using the smooth language of planetary orbits. A new perspective was required, a way to tame the erratic behavior of the primes and render them susceptible to analytical investigation. Chebyshev's genius was to find precisely this perspective. He understood that a direct assault on the prime counting function was likely to fail. His solution was to study related weighted sums that were better behaved. He introduced two now famous auxiliary functions. The first, the Chebyshev theta function, denoted as theta of x, is defined as the sum of the natural logarithms of all prime numbers less than or equal to x. The second, the psi function, psi of x, is the sum of the natural logarithms of all prime powers, that is, p to the power of k, that are less than or equal to x. The introduction of the logarithm was a masterstroke. Logarithms possess the crucial algebraic property of converting products into sums, and they grow much more slowly than the numbers they are applied to. By summing the logarithms of primes, Chebyshev created functions that were smoother and more closely tied to the integral calculus than the raw count of primes. The psi function, in particular, which accounts for the influence of higher prime powers, proved to be the more powerful tool. These functions effectively act as a proxy for the prime distribution, carrying the same essential information as pi of x, but in a form more amenable to the machinery of analysis. Armed with these new instruments, Chebyshev achieved the first substantial progress on the prime number theorem in over 50 years. He first established a profound connection between his pi function and the original prime counting function, showing that the asymptotic behavior of one was equivalent to the other. He then proved a spectacular result. If the limit of the ratio of pi of x to x, divided by the natural logarithm of x, exists as x approaches infinity, then that limit must be equal to 1. This single piece of work transformed the prime number theorem from a numerological curiosity into a concrete analytical problem. The question was now focused: does this specific limit exist? The grand conjecture now rested on a tangible analytical foundation. This accomplishment alone would have secured his place in the history of number theory. Yet he pressed further. His next result was even more consequential, providing the first rigorous quantitative constraints on the density of primes. Known today as Chebyshev's theorem, he proved that the function pi of x is permanently sandwiched between two constant multiples of the conjectured approximation. He demonstrated that for all sufficiently large x, pi of x is bounded below by a constant c, 1 times x divided by the natural logarithm of x, and bounded above by a constant c, 2 times x divided by the natural logarithm of x. Crucially, Chebyshev calculated explicit numerical values for these bounding constants. He showed that the lower constant is approximately 0.921, and the upper constant is approximately 1.105. This was a revelation. It meant the primes could neither be too sparse nor too crowded. Their distribution, while locally unpredictable, had to obey this global asymptotic law. The prime number theorem, if true, meant that these two constants would eventually squeeze together and converge to one. Chebyshev had built the analytical cage. The ultimate proof would involve showing that the cage shrinks to a single point. The immediate power of these bounds was demonstrated when Chebyshev used them to provide the first-ever proof of a related long-standing conjecture known as Bertrand's postulate. First proposed by Joseph Bertrand in 1845, after checking it for millions of numbers, the postulate asserts that for any integer n greater than 1, there is always at least one prime number p, such that p is greater than n and less than 2n. It is a guarantee of a certain local density of primes, a promise that the gaps between them can never become too large. Using his newly established upper and lower bounds for the prime counting function, Chebyshev was able to show that the number of primes between n and 2n, which is given by p of 2n minus p of n, must always be greater than 0. The proof was a stunning display of the utility of his new methods, resolving a famous open problem as a direct consequence of his deeper investigation into the global distribution of primes. The ultimate proof of the prime number theorem itself remained elusive in his lifetime. It would require the development of sophisticated techniques in complex analysis, a field whose power was beginning to be explored. The final victory would belong to Jacques Hadamard and Charles de la Vallée-Poussin, who, working independently in 1896, used these advanced methods to show that Chebyshev's limit does indeed exist and is equal to 1. Their proofs, however, relied explicitly on the conceptual framework he had built. They worked with his psi function, and their arguments followed the analytical pathway he had first cleared. Chebyshev had taken the chaotic wilderness of the prime numbers and carved out the foundational roads and bridges upon which all future explorers would travel. He had demonstrated that the problem was tractable, transforming it into a central question of analytic number theory and providing the essential tools that would lead to its final resolution. His approach, wedding elementary methods with profound insight, stands as a landmark in the quest to understand arithmetic's deepest secrets, a testament to a mind capable of seeing order where others saw only chaos. The same powerful impulse to find the ideal form within a world of practical constraints would soon guide his work into the tangible realm of mechanics and engineering. The powerful impulse to find the ideal form within a world of practical constraints, which had guided Pafnuty Chebyshev's assault on the distribution of prime numbers, soon found a new and profoundly tangible domain. His attention turned from the discrete realm of integers to the continuous world of functions and the very real machinery of the industrial age. Here, a parallel challenge existed. While mathematicians possessed tools of extraordinary precision for describing functions locally, the ability to capture a function's global behavior with a simple, useful approximation remained an elusive and urgent goal. The creation of astronomical and logarithmic tables, the bedrock of computation for science and engineering, demanded functions that were both accurate and calculable. The prevailing method, the Taylor series expansion, provided a polynomial that was a perfect mimic of a function at a single point, but its fidelity decayed, often precipitously, as one moved away from that point of contact. A different kind of perfection was needed, a polynomial that would be the best possible compromise across an entire interval, a faithful companion to a complex function over its whole journey. This search for a globally optimal approximation became the central problem that would lead Chebyshev to erect an entirely new edifice within mathematics, the theory of best uniform approximation. He began by fundamentally reframing the question of what constituted a best fit. The prevailing statistical idea of minimizing the sum of squared errors, which averages out discrepancies, was insufficient for his purposes. An engineer using a faulty logarithm table cares little that the errors are small on average if a single catastrophic error exists at the specific value they need. Consequently, Chebyshev pursued a more stringent and practical criterion. He sought the one polynomial of a given degree that minimized the maximum absolute difference between itself and the target function over a specified interval. This is the challenge of minimizing what is now called the uniform norm or the L-infinity norm. The goal was to find an approximation whose largest error was as small as it could possibly be, guaranteeing a certain level of accuracy everywhere. His solution to this problem was as elegant as it was profound, and it rested upon a remarkable family of functions that now bear his name, the Chebyshev polynomials of the first kind. These are typically denoted T sub n of x. While they are polynomials in x, their most intuitive definition lies in trigonometry. The polynomial T sub n of x is defined by the identity that T sub n of the cosine of an angle, theta, is equal to the cosine of n times that angle. This seemingly simple relation imbues these polynomials with extraordinary properties. On the interval from -1 to 1, they oscillate between -1 and 1, reaching their extreme values multiple times. This oscillatory behavior is the key. Chebyshev proved a foundational result, now known as the equioscillation theorem, which provides a stunningly beautiful condition for an approximating polynomial to be the best in the uniform sense. The theorem states that a polynomial, let us call it P of x, is the best uniform approximation to a continuous function, f of x, if and only if. The error function, f of x minus p of x, alternates between its maximum and minimum absolute values, at least n plus 2 times, where n is the degree of the polynomial. Visually, this means the graph of the error function must wobble perfectly, touching the horizontal lines representing the maximum positive and negative error in a regular alternating pattern. This equioscillation is the signature of optimality. It ensures that the error is distributed as evenly as possible across the interval, with no single region bearing a disproportionate share of the inaccuracy. With this theorem, Chebyshev had provided a definitive certificate of quality for an approximation, transforming an art into a science. The legacy of this theoretical breakthrough is immense and continues to permeate modern science and engineering. Chebyshev polynomials are a cornerstone of numerical analysis, forming a superior basis for representing functions in computer algorithms compared to the standard power series. Their unique properties are exploited in spectral methods for solving differential equations with incredible accuracy. Beyond computation, this work finds a surprising and powerful echo in electrical engineering. The design of high-performance electronic filters, devices that must allow signals of certain frequencies to pass while sharply rejecting others, often relies on a design principle called a Chebyshev filter. The frequency response of such a filter exhibits the very same equioscillation property in its passband, allowing for a much steeper transition or roll-off than other designs of similar complexity. The ripples in the filter's performance are a direct electronic analog of the oscillating error in his optimal polynomials. This drive to connect abstract mathematical optimality with concrete physical utility reached its zenith in Chebyshev's celebrated work on mechanics. In the age of steam, One of the most persistent challenges for engineers was the problem of linkage kinematics. The steam engine's piston needed to move in a straight line, but the crankshaft that drove it moved in a circle. The engineering ideal was to convert perfect rotational motion into perfect linear motion using a simple, robust system of rigid rods and pivots. While an exact solution, the Poisselier-Lipkin linkage, was discovered, it was complex. A simpler mechanism that produced an approximately straight line was often more practical. The question then became, what is the best approximate straight-line linkage? For Chebyshev, this was a familiar problem in a new guise. He recognized that the path traced by a point on a mechanical linkage could be described by an algebraic curve. The engineering challenge of designing a straight-line mechanism was therefore equivalent to the mathematical problem of finding a linkage whose curve was the best polynomial approximation to a straight line over a given range of motion. He brought the full force of his approximation theory to bear on this mechanical puzzle. The result was a series of ingenious inventions, the most famous of which is the Chebyshev linkage. This is a simple four-bar mechanism, a collection of three moving links connected to a fixed base. By carefully choosing the lengths of these links according to the principles of his approximation theory, Chebyshev designed a device where a point on the central link traces a path that is astonishingly close to a straight line through a significant portion of its travel. The path deviates, of course, but it deviates in a controlled, optimal way, exhibiting the characteristic equioscillation of his mathematical theory. He also developed other mechanisms, like the lambda mechanism, which performed a similar function, demonstrating a systematic program for the mathematical synthesis of machines. This fusion of abstract functional analysis and practical mechanical design was a landmark achievement, illustrating a powerful new paradigm where pure mathematics could serve as the direct blueprint for optimal engineering. The same intellectual framework that guaranteed the quality of a logarithm in a table could now guarantee the quality of motion in a steam engine. This philosophy, which saw profound theoretical questions embedded within the practical challenges of the physical world, would become the animating spirit of the entire school of thought he was meticulously constructing in St. Petersburg. This intellectual spirit, which located profound mathematical truths within the tangible world of machines and measurements, became the bedrock of the institution Chebyshev built around himself. So, Petersburg Mathematical School was a direct reflection of its founder's mind, rigorous, pragmatic, and perpetually concerned with the concrete. His lectures at the University of St. Petersburg, which he delivered for over 3 decades, were legendary for their clarity and their demanding nature. He fostered an environment where abstraction served application and where a beautiful theorem was one that provided a tangible quantitative grip on a problem. He insisted on proofs that were constructive, yielding algorithms and explicit error bounds, viewing existence proofs that failed to provide a method of finding the object in question with a certain academic suspicion. For Chebyshev, the goal of mathematics was to provide answers, and those answers had to be accompanied by a guarantee of their quality. This philosophy permeated his mentorship, shaping a generation of Russian mathematicians who carried his intellectual DNA forward. He cultivated talent with a discerning eye, guiding his most promising students toward problems that were both fundamental and deeply connected to his own research program. He would present a problem, often one he himself had been pondering, and encourage his protégés to attack it, offering guidance while demanding originality. The result was an intellectual dynasty, a lineage of thinkers who extended his work into domains he had only begun to chart. 2 figures in particular stand as monumental pillars of his pedagogical legacy: Andrei Markov and Alexander Lyapunov. Each took a core element of Chebyshev's work, and under his guidance transformed it into a new and powerful branch of mathematics.
Andrei Markov became the great heir to Chebyshev's probabilistic world. His mentor had forged powerful tools for understanding the collective behavior of large numbers of independent random variables. The Chebyshev inequality and his version of the law of large numbers provided rigorous bounds on the behavior of systems where each event was a fresh roll of the dice, uninfluenced by what came before. Markov, absorbing this framework, turned his attention to a subtler and vastly more common class of phenomena, systems where the future depends on the present. He asked what could be said about a sequence of events where the probability of the next outcome is conditioned by the current state. This inquiry led to his seminal 1906 paper on what we now call Markov chains. He developed the mathematical formalism for a sequence of random variables where the probability distribution of the next state depends only on the current state. This was a direct, brilliant generalization of the world Chebyshev had explored. A Markov chain is, in essence, a system with a one-step memory. The classic example is a metaphorical frog hopping between lily pads, where its choice of the next pad depends only on which pad it currently occupies, and its entire history of previous hops is irrelevant. Markov proved that under certain reasonable conditions, such systems also exhibit long-term stable behavior. They converge to a stationary distribution, a probabilistic equilibrium that is the conceptual cousin of the convergence described in the law of large numbers. He had extended his mentor's quest for certainty amid randomness into the realm of dependent processes, creating a tool of astonishing versatility. From modeling the weather to predicting stock market movements, from analyzing language structure in a text to the algorithms that power Google's PageRank, the concept of the Markov chain is a cornerstone of modern statistics and computer science, a direct intellectual continuation of the probabilistic questions first posed with such rigor by Chebyshev. While Markov extended the reach of probability, Alexander Lyapunov took up the mantle of Chebyshev's analytical mechanics and approximation theory. Lyapunov was fascinated by the question of stability. It is one of the most fundamental inquiries in all of science. If a system in equilibrium is slightly perturbed, will it return to its original state, or will it diverge, perhaps catastrophically? Think of a marble resting at the bottom of a bowl versus one balanced precariously on top. Both are in equilibrium, but their responses to a small nudge are entirely different. The problem had deep roots in celestial mechanics, particularly in questions about the long-term stability of the solar system, but it was also central to the control of machines, a subject dear to Chebyshev's heart. Lyapunov, armed with the powerful analytical tools of inequalities and approximation methods, championed by his teacher, developed a comprehensive and profoundly original theory of stability for systems of differential equations. His doctoral thesis in 1892, The General Problem of the Stability of Motion, is one of the great landmarks of mathematical physics. He introduced what is now known as the Lyapunov function, a scalar function whose properties can determine the stability of a system without requiring the explicit solution of the differential equations themselves. If one can find a function that is always positive and whose value decreases along any trajectory of the system, much like the energy of a physical system with friction, then the system is guaranteed to be stable. This ingenious method transformed the problem of stability from one of intractable calculation into a search for an appropriate auxiliary function. It was a move of profound abstraction that, in true Chebyshevian spirit, yielded immensely practical results. Lyapunov's stability theory became the bedrock of modern control theory, essential for designing everything from aerospace guidance systems to stable chemical reactors and resilient power grids. He had taken the spirit of Chebyshev's quest for bounds and optimal control and elevated it into a general rigorous theory of dynamic behavior. The quest for the optimal bound, the most efficient approximation, the most probable outcome, this was the unifying pulse of Chebyshev's life's work. His intellectual legacy is a testament to the power of a single unifying perspective, applied with relentless genius across disparate fields. From the enigmatic distribution of prime numbers, where he established the first effective bounds on their count, to the unpredictable world of chance, where his inequality placed a firm limit on deviation, he sought to constrain the unknown. In the abstract realm of functions, he discovered the unique polynomials that hugged a curve with minimal error. And in the concrete world of engineering, he translated that same principle into iron and steel, designing mechanical linkages that produced the best possible approximation of a straight line. He saw a world of abstract challenges awaiting concrete quantitative answers. This pragmatic, powerful, and uniquely constructive approach became the defining characteristic of his mathematical school, cementing a legacy that extends far beyond his individual theorems to the very methodology of modern applied mathematics, statistics, and engineering, forever shaping our ability to find order, efficiency, and certainty within a complex world.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.